Hello students, today we will discuss about electric potential. This is the second chapter in electrostatics, electric potential and capacitance. Electric potential, like gravitational potential, how it was defined as it is the amount of work done in bringing unit mass from infinity to any point in gravitational field. Exactly in the same way, electric potential due to any charge at any point is defined as the amount of work done in bringing unit charge from infinity to that point. As it is the amount of work done, so it is a scalar quantity. Its SI unit is volt, represented by symbol V. See, the electric potential, for that also symbol is V. Its SI unit is also having symbol V. Also it is as work done in bringing unit charge, that's a joule per coulomb. Also you can write Newton meter per coulomb. So various units you can write for this. Electric potential due to positive charge can be positive, due to negative charge it can be negative. Now we will derive the equation for electric potential due to point charge. So here let us consider any charge Q. This is the charge which is producing electric field around it, and we want to find electric potential at any point P due to this charge Q, which is at a distance r from point P. So according to definition of potential, it is the amount of work done in bringing unit charge from infinity to point P. Here we will bring charge Q0 from infinity to point P. This charge Q0 we will call it as a test charge. So consider a point charge Q placed in a space to find electric potential due to Q at any point P at a distance r from the charge Q. Calculate the work done in bringing test charge from infinity to point P. Work done in bringing charge Q0 from infinity to point P, you can calculate as integration of dw. Why it is integration? Because you know that electrostatic force, it is a distance varying. As distance changes, electric force also changes. So it is a variable force, and that's why to find the work done, we have to divide the whole path into small line elements. Let's say each of element of length dx, that the distance of element dx from charge Q, if it is x, then at this point at a distance x, force acting on Q0 due to Q, it is repulsive force, whereas displacement we make that is toward the charge, and that's why force and displacement both are in opposite direction. As they are in opposite direction, angle between them is 180 degree. So dw is equal to f dot dx. When we find f dot dx is f dx cos 180, electrostatic force is kq q0 by x square, dx cos 180 is minus 1. So here for the small displacement dx, work done is kq q0 by x square dx. Okay. We want to find the work done in moving charge from infinity to up to point P. So we will integrate over the range infinity to point P. Infinity, that is at a distance infinity, point P is up to distance r. So range of integration for x, that is from infinity to r. Now if you integrate this here, kq q0, that is constant, negative sign also taken outside, 1 by x square, integration of that is minus 1 upon x, limit from infinity to r. So if you put the values here, it is 1 by r minus 1 by infinity, negative sign that is cancelled. So what is left, that is w is equal to kq q0 by r. So this is the work done in moving charge q0 from infinity to point P in presence of charge q. As electric potential is defined as the work done in bringing unit charge, that's why we will divide this work done with the charge Q0 which is moved, and that's a W by Q0, that will give you the electric potential at point P due to charge Q. So if you divide it by Q0, then what is left, that is KQ by R. So that way you can say electric potential due to point charge, it is directly proportional to magnitude of charge, it is inversely proportional to the distance. V is equal to KQ by R. It also depends on, we can say, medium in which the charge is placed. If Q is positive, then electric potential due to charge is positive. If Q is negative, electric potential also negative. If charge Q is 0, then electric potential is 0. So we can say that electric potential is a scalar quantity. It can be positive, it can be negative, it can be 0 also. That depends on the value of charge. So this way you can find electric potential due to a point charge. Next is electric potential. Electric potential difference, it is represented by symbol delta V. Again, it is a scalar quantity, unit is volt. Electric potential difference between any 2 points in electric field due to any charge is defined as the amount of work done in moving unit charge from one point to another. Let us consider here charge Q is there, it is producing electric field around it, and we want to find electric potential between points A and B. According to the definition, it is the amount of work done in moving unit charge from point A to point B. Let us consider charge Q0, which is moved from point A to point B. What amount of work is done here? So you know that work done in bringing unit charge or charge Q0 from infinity to point A is KQ Q0 by R suffix A. Similarly, work done in moving charge from infinity to up to point B is KQ Q0 upon RB. So we can say that work done in moving charge from point A to B is work done in moving Q0 from point A to point B is WAB is equal to WB minus WA. That is KQ Q0 1 upon RB minus 1 upon RA. And potential difference, as it is the amount of work done in moving unit charge, and that's why you can write potential difference delta V, that is VB minus VA. Final position is B, initial position is A. So final potential minus initial potential. VB minus VA, that is WAB by Q0. And if you put this value divided by Q0, you get KQ into 1 upon RB minus 1 upon RA. Now as you know, from the diagram, point A is closer to point charge Q, point B is far away. So RA is greater than less than RB is greater than RA. RB is greater than RA, that's why VB is less than VA. It means that VB minus VA is negative. It means you can say that as you move in the direction of electric field, electric potential decreases. Relation between electric field and electric potential. Let us consider, suppose this charge Q is there. Due to this charge Q, this positive electric field is readily outward. 2 points A and B, if we consider point A, it is at a distance R suffix A, point B is at a distance R suffix B. If we want to move any charge Q0 from point A to B by displacement delta R, the amount of work done is calculated as WAB is equal to integration F dot dr. Using this equation you can calculate. And you know that F is equal to Q naught E, so Q naught E dot dr, and from that you can find WAB by Q naught is equal to E dot dr. Here potential at point A, that is VA, potential at point B is VB. As point A is closer, so VA is greater than VB. And that's why when we say potential difference between points A and B in moving charge from A to B, that is potential difference delta V, that is final potential minus initial potential, WAB by Q0 is equal to VB minus VA. We have these two equations of WAB by Q0. If we equate these two, we can write E dot dr is equal to, this is equal to delta V, but this delta V is, as VB is less compared to VA, that's why delta V is negative, and that's why you can write E into dr is equal to minus dV, or E is equal to minus dV by dr. This is what we can say, it is a relation between electric field and electric potential difference. Say what it means, that is negative sign, what negates that? In the direction of electric field, electric potential decreases, whether the charge is positive or negative. Next is equipotential surface. Equipotential, it means that the potential is same, equal at every point on the surface. So equipotential surface, it is the imaginary surface drawn around a charge such that the electric potential at every point on the surface is equal. Let if we consider suppose a point charge, let's say Q greater than 0 or Q less than 0. You know that for a point charge, electric potential equation is given as V is KQ by R. So at a distance R, from the charge Q at an equal distance R, you consider all the points around the charge. On all the points, electric potential will be same. So locus of all that point that we call as equipotential surface. So if you want to draw equipotential surface for any charge, infinite surfaces you can draw, okay, having different radius. But to draw the equipotential surface, as we have this relation dV is equal to minus E into dr, we draw the equipotential surface keeping the potential difference between two consecutive surfaces equal. Now, this LHS, if you want to keep constant, what is their RHS? Here it is a product of E and dr. You know that due to the charge, electric field decreases as you move away from the charge, and that's why as you move away from the charge, spacing between two equipotential surfaces will increase, and that's why the equipotential surface which are drawn, as the radius increases, the spacing between two equipotential surfaces gradually increases, such that potential difference between any two consecutive surfaces that always remains same. So this way you can draw equipotential surface for point charge. Properties of equipotential surface. Equipotential surface are concentric spheres for point charges. Two equipotential surfaces never intersect each other. You know, equipotential surface represents the electric potential at any point on its surface. If they are intersecting, means two different surfaces are intersecting, it means that at the point of intersection there are two values of electric potential, which is not possible. And that's why we can see two equipotential surfaces never intersect each other. If there are a system of charges, then equipotential surface, due to that, either they repel each other or they attract each other. Here you can see it is attraction, here it is repulsion. If they attract each other, they are due to like charges. If they repel each other, they are due to unlike charges. And that's why for a system of charges, like charge, if it is equipotential surfaces are bulging inside, for unlike charges, equipotential surfaces are bulging outside. Another thing, relative spacing between the equipotential surface represents strength of electric field in that region. It means that if two equipotential surfaces are closer to each other, means that in that region electric field is stronger. If spacing is more, then in that region field strength is less. You can see here near the charge, the equipotential surfaces are closer to each other, means that in this region electric field strength is more. Here electric field strength is less. Another one thing, work done in moving charge on equipotential surface is always zero. We know that work done is equal to potential difference into the charge moved. If equipotential surface is there, potential difference between any 2 points, it is same, and potential is same, so potential difference is zero, and that's work done is also zero. So we can say no work is done in moving the charge on equipotential surface. You can take the example like suppose electron is revolving around the nucleus of an atom. Due to the positive charge of the nucleus around it, the equipotential surface is there and the electron is moving on that equipotential surface. So no work is done in doing this process, and that's why we say electron is, when it is revolving, it is not radiating energy. Another is equipotential surfaces are always normal to electric field lines at every point. Again, with this concept also you can say when the electric field and equipotential surface are normal to each other, and we know that work is equal to force into displacement, and that is nothing but W is equal to F dot dr, and that is equal to Q naught E into dr. As E and dr, electric field and equipotential surface, if they are perpendicular, E dot dr, angle between them will be 90 degree, cos 90 is 0, so work done will be also 0. Or we can say that electric field lines, they are always normal to equipotential surface at every point. So these are the various, we can say, properties of equipotential surface.